The fraternal twin evils of bias and variance. That phrase, it just perfectly captures the fundamental struggle every single data scientist faces, doesn't it? It's not enough to just train a model. You've got to find that delicate, almost impossible balance where your algorithm isn't overly simplistic, but, and here's the kicker, it also isn't hallucinating patterns out of pure noise. Today, we're going to look at exactly how to defeat these twin evils once and for all.
Welcome to this explainer. Today, we're essentially building a mathematical arsenal. Our main enemy here? Overfitting. We're going to use a structured framework built right on top of core machine learning concepts to automatically select the absolute best model for any given dataset. And we aren't just skimming the surface, learning what these tools are. We're getting into exactly how and why they work to completely bulletproof your algorithms. Okay, let's look at the roadmap for today. First, the twin evils. Then we'll hit cross-validation. Third, feature selection. And finally, number 4, the Bayesian approach. Let's dive in.
Section 1. The fraternal twin evils.
So here's the big question. How can we automatically select a model? It sounds simple enough, right? But it's actually incredibly complex. Let's say you're trying to select the degree of a polynomial regression model. Should it be a degree of 1, 2, or maybe 10? Or maybe you're trying to find the right bandwidth parameter for a locally weighted regression, or that elusive C parameter for an L1 regularized support vector machine. What we're really looking for is that Goldilocks fit. Not too biased, not too high variance, just perfectly right.
Now, your very first instinct might be to use naive empirical risk minimization. That basically means you train all your candidate models, you look at which one has the absolute lowest error on the training data, and you just pick that one. But actually, scratch that. This is a massive trap. If you do this with, say, polynomial regression, the method is basically hardwired to always select the highest degree polynomial possible. Why? Because it perfectly memorizes the training data. But the second you apply it to new, unseen data, it fails miserably. That is classic high-variance overfitting. The truth is, we really don't care about training error. What we actually care about is generalization error.
Which brings us to Section 2, Mastering Cross-Validation. Let's take a look at the most basic form of this, which is holdout cross-validation. Some people call it simple cross-validation. The logic here is just brilliant in its simplicity. Step 1, you take your entire data set and you randomly split it into 2 chunks, a training set and a holdout cross-validation set. Step 2, you train all your candidate models strictly on that training data. And step 3, you test them on the holdout set and just pick the one with the smallest error. By forcing the models to test on unseen data, we get a much truer estimate of a model's actual generalization error.
But you'll probably notice the prominent number 30 here. Typically, standard practice is to use 30% of our data for that holdout set, which leaves 70% for training. But there's a pretty glaring problem with this. It wastes almost a third of your data. Now, if data is super abundant, sure, that's fine. But what if you have a tiny data set? Say, literally only 20 examples. Tossing away 30% of that just for testing is a total luxury you just cannot afford.
So clearly we need an upgrade. Let's contrast this data-heavy holdout method against a highly efficient technique that actually recycles our data. It's called K-fold cross-validation. So in K-fold cross-validation, you take your data and split it into K equal disjoint subsets. Then you loop through them. For every single subset, you hold it out as your test set, and you train your model on all the other subsets combined. You literally do this K times and then average the estimated errors out at the end. In really extreme cases where data is incredibly scarce, you can take this to the max and hold out just one single data point at a time. We call that leave one out cross-validation.
Now, out in the real world, in industry practice, the standard heuristic choice for the number of folds is 10, so 10-fold cross-validation. This means you're only holding out 10% of your data at any given time. It's definitely a trade-off. It's computationally way more expensive because, well, you have to train every single model 10 separate times, but it squeezes absolutely every drop of value out of your precious data.
All right, Section 3, Smart Feature Selection.
Imagine you're tackling a supervised learning problem, and your number of features vastly exceeds your actual number of examples. Maybe you're doing text classification with a massive vocabulary. Overfitting is practically guaranteed here unless you aggressively trim down your features. But how do you decide how many features to actually keep? Well, if you have n features, there are literally 2 to the power of n possible combinations. It is mathematically impossible to manually check all 2 to the power of n subsets. Just no way. To get around this, we usually rely on 2 main categories of feature selection: wrapper methods and filter methods. And it's really important to understand the trade-offs between them here. Wrapper methods are computationally very expensive, whereas filter methods are much cheaper, but they do rely heavily on heuristics. Let's look at a classic wrapper method first, forward search. You basically start with an empty set of features. Then, you iteratively test adding each available feature one by one using cross-validation to see which single addition improves your model the most. You lock that winning feature in, and then repeat the whole process to find the second best feature, and so on. It literally wraps around your learning algorithm. But, fair warning, doing a complete forward search requires O of n squared calls to your learning algorithm. In plain English, it is incredibly slow, super resource intensive, and frankly a total nightmare for massive datasets. Because wrapper methods can be so agonizingly slow, we often pivot to filter methods instead. Here, we compute a score called mutual information, or MI. Mathematically speaking, this acts as a Kullback Leibler, or KL divergence. You can think of it kind of like a lie detector for your data. It measures exactly how far a feature is from being entirely independent of the target class label. If a feature and the label have absolutely zero connection, the score is just 0. This is awesome because it lets us quickly filter out all the useless noise and keep only the features that actually help predict our target.
Moving on to Section 4, the Bayesian approach. To really understand this one, we have to look at two totally contrasting philosophical views of statistics. The frequentist view, which relies on maximum likelihood, assumes that the parameter we're trying to find is an unknown but constant value in the real world. It's basically just a fixed number that we haven't figured out yet. The Bayesian view, on the other hand, completely flips this on its head. It says the parameter itself is a random variable, complete with its own prior distribution. What this means is we can actually inject our own prior beliefs into the math before we even glance at the training data.
So, the crucial point here is how we actually calculate our parameters using this Bayesian worldview. Doing a fully Bayesian prediction is computationally terrifying. I mean, it requires taking integrals over high-dimensional spaces that very rarely have closed-form solutions. So instead, we approximate it using the maximum a posteriori, or MAP, estimate. It gives us a really practical point estimate by taking the standard maximum likelihood formula and simply multiplying it by our prior distribution.
Now you might be wondering, how does simply multiplying by a prior actually stop overfitting? Well, in practice, we often assume our parameters follow a Gaussian distribution centered exactly at 0. By injecting this specific prior, we are mathematically forcing the fitted parameters to have a much smaller norm. We are quite literally tying them down and pulling them closer to 0, which forcefully restrains the model from becoming wildly complex. This is exactly why Bayesian logistic regression is so incredibly effective for stuff like text classification. The prior protects the algorithm from overfitting, even when you have thousands more features than actual data points. It's a real game changer.
And finally, Section 5, winning the overfitting battle.
Let's take a step back and look at the complete arsenal we've built from the source material today. You don't just pick one of these tools, you use them all in concert, the whole shebang. You use cross-validation, like that tenfold method, to fairly test your models on unseen data. You use feature selection, whether that's wrapper or filter methods, to aggressively trim away the noise and reduce the sheer complexity of your data. And then you use the Bayesian MAP estimate to mathematically regularize your model, restraining its parameters with those prior distributions. Together, these three distinct tools work perfectly to ensure you get a robust, generalized model that completely defeats both bias and variance.
Because let's face it, out in the wild, data is rarely clean, and models will always naturally try to memorize things rather than actually learn them. It is entirely up to you to force them to generalize. So I'll leave you with this final thought. Which mathematical weapon are you going to deploy on your next messy dataset? Thanks for joining me for this explainer, and keep learning.